All right, so let's get back to work again here. So a quadratic form is a mapping from, it takes in a variable, n variable from Rn, and outputs a real number. It has a formula which looks like this: x transpose ax, where without loss of generality we assume that, I mean, this, I'm making it part of the definition just to get it over with. A transpose has to be equal to A, so I assume that this matrix is symmetric. This gives us what's called a quadratic form, and the matrix of the quadratic form is A. So a couple examples. Example 1. The quadratic form x squared plus y squared has matrix, you can multiply this out and get back to that. The matrix is the identity matrix. Great. Another example. The quadratic form with formula, 2x, x squared plus 2xy plus 3y squared. This 2xy gives me both of these 1's, okay? And 1, this 3 goes there like that, so the matrix is 1, 1, 1, 3. Okay. Let's see here, let's look at a kind of a little bit uglier example. X squared plus 2xy minus y squared minus 2xe plus 7z squared. So suppose you have this formula. That's a quadratic form. Basically, the quadratic form is a formula that just has second degree polynomials in however many variables you're looking at. All right. Every term has degree 2. It's either formed from a square or from a product of two variables in the set. All right, it's a quadratic form. But it's convenient to say that it's written in terms of a symmetric matrix like this. Now, this 2xy is giving me these two red ones. This minus 2xe is giving me these two green minus 1's. The fact that there is no yz term is giving me these zeros. The diagonals are coming from the squares, x squared, the minus y squared, and the 7z squared. All right, there you go. I think anybody can do this without too much trouble. Now, quadratic forms are amazing in terms of their structure. It's really quite beautiful. And a little bit surprising that linear algebra has so much to say about it, because they are, after all, nonlinear, and yet they're still governed by a matrix, which means linear algebra has much to say. Here's the theory in brief. If we write, I'm saying v is the magnitude, v hat is the vector direction, the unit, so v hat's the unit vector. So, oh, I'm sorry, I'm missing, oopsie, missing some, there, fixed, okay. So vector divided by direction gives me, vector divided by magnitude gives me a unit vector. I can put a hat on it. So that's a typical element of the n-1 sphere inside Rn. And so what this formula says, and it's easy to work this out from the definition because it's matrix multiplication, right? So you just go back up here and you got magnitude, pull it out, you got square magnitude, and you're left with unit vector transpose A unit vector, which is, that's Q of unit vector. So that's it. But the interesting thing here is that the values of the quadratic form are governed, they're fixed by whatever happens on the n-1 sphere. So basically, if you have a quadratic form in the plane, if you look at the unit circle, then whatever happens to the values of the quadratic form on the unit circle, they pretty much govern whatever happens on out there, just according to, like, if this is 3, if I go out here to, say, distance 4, then I would have 3 times 4 squared. That would be, whatever that is, 48. Knowing that the quadratic form has value 3 there forces that to be 48 out there, supposing this is the unit circle. All right. So that's kind of interesting, or boring. Then here's why we make it symmetric. If it's a symmetric matrix, then you're actually going to prove this using Lagrange multipliers in your homework. Then there exists a set of vectors and a set of numbers called eigenvalues, lambda 1 through lambda n, such that this is what makes it an eigenvector, that A times vi is lambda vi. And more than that, you can, and maybe I didn't make you prove this part, but it can be shown that you can choose them to be an orthonormal eigenbasis, which means that they're, orthonormal. And if you do that, you work through it, you get that P transpose AP is the diagonal matrix, which results in us being able to write a formula. If you express the quadratic form in terms of the eigencoordinates, then the formula is just lambda 1 y1 squared plus lambda 2 y2 squared plus lambda n yn squared, which is just so much simpler than something like that. You know, there's only squares, no mixing, so it's easy to figure out what's maximum, what's minimum. In particular, if we take the set of eigenvalues, which is known as the spectrum, and we order them smallest to largest, so lambda 1 less than lambda 2, less than lambda n. By the way, these are real numbers. That's part of the real spectral theorem. Then we can argue, since q tilde, all right, which is, again, the formula for the quadratic form in terms of eigencoordinates, which is this. Well, think about it. If we're on Sn minus 1, what's the biggest that the coordinates can be? Well, plus or minus 1, right? So the smallest value we can take is when we make y1 be 0 and make all of the y1 be 1 or minus 1, make all of these 0, then that gets us lambda 1, which is the smallest thing. If we make all of these 0 except for yn and make that 1, that gives us the largest thing. So these are the extreme values of the quadratic form on the n minus 1 sphere. So the punchline is that the eigenvalues of the quadratic form describe the min-max of Q restricted to the Sn minus 1 sphere. The neat thing is, guys, it's relatively easy to calculate eigenvalues. It's the eigenvector calculation I kind of shy away from for you guys. So let's calculate an eigenvalue and see how it's interesting. Here's an example. Suppose we've got the quadratic form x squared plus 4xy minus y squared plus 3z squared, all right, which would have this matrix. So to calculate the eigenvalues, what you want to do is calculate the characteristic equation. The way this is done is you take the determinant a matrix you're looking at, you subtract lambda times the identity, and then you calculate the determinant of that, set it equal to 0. The solutions to that equation are called eigenvalues. So I work out the algebra here, and it works out to, if I didn't make a mistake, I hope I didn't, lambda squared minus 5 times 3 minus lambda, which factors like so. So my smallest is minus root 5, my next biggest is root 5, about 2.2-ish, and then 3, so this is my spectrum. Minus root 5, 3. So that says to me that this expression is between minus 5 and 3, provided that x squared plus y squared plus z squared equals to 1. To quote my son Daniel, yikes. I mean, that's wow. That's, I don't know, that seems kind of like a tough inequality to prove from this to that. I don't know. I mean, like, I think that ain't bad. That ain't bad. So, all right, that's it. So when we're faced with a quadratic form, what we learn here, calculate the eigenvalues. You can do it. Your homework problem proves that they exist and they're real, and that, anyway, the eigenvalues maximize the quadratic form on the n minus 1 sphere. That's pretty much all we need to really analyze multivariate power series carefully. So that's next, and I'll get right to it in a second. Thanks, guys.